Okay, the notes for today cover sampling distributions, and then we're going to obviously talk about this some more tomorrow as well. But a blank is a number describing a blank. This is going to be a parameter is a number describing a population, and then I have a sample is a number describing, a statistic, is a number describing a sample. Okay, and you kind of can tell by the way they were named. A parameter describes a population, a statistic describes a sample. But what do we mean when we say parameter or statistic? So let me give you some examples. A parameter is usually given a symbol, and that symbol is usually going to be the Greek letters. So we have mu, not always, but usually. So this is going to be the population mean. As opposed to a statistic, it would be the sample mean. So I'll just kind of help you see what the differences are here. And then we also could have sigma, which is going to be the population standard deviation, as opposed to S, which is going to be our sample standard deviation. We could have capital N, which is our population size. So in the German tank problem, we're kind of trying to estimate our capital N, the population size. And then for the for the sample, it's N, which is the sample size. And then we also have a population parameter called P, which is a proportion. So P, I don't know why that's doing that, P, which is going to be a population proportion. So you might want to know the true proportion of the population that plans to vote in the upcoming election. And you may not actually have that information, but you would have something referred to as P hat, which is the sample proportion, and you would use the sample proportion P hat to estimate the population proportion P. So I tried to make a direct comparison between the sample statistic and the population parameter because usually the parameter is unknown, and you usually use your sample statistic to estimate the population parameter. So we use a sample statistic to estimate a population parameter. So if we're interested in the true mean of the population, we would use the sample mean x bar as an estimate of the population mean u. And that's essentially what we're trying to do in the German tank problem that we've been working on, except you use formulas. So you use a statistic, a sample statistic, and somehow modify that to estimate the size of the population. All right, so you have to be able to identify the population, the sample, the parameter, and the statistic. So let's look at the first example here. So identify the population, parameter, sample, and statistic in each of the following. A pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates Q3 to be 56 inches. Okay, so the population is all 10-year-old boys. Okay, and we are interested in, from that population, the parameter is the 75th percentile for all 10-year-old boys. Now the sample is just the 50 patients. And the statistic is going to be Q3, and that is actually equal to 56 inches from the sample of 50 patients. So from the sample of 50 patients. So pretty straightforward, but you have to read all the words and make sure you know what you're doing there. Okay, so I want you to try part B here on your own and then check back in just a minute. So just pause it and check back in just a minute. Okay, so a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So the population is going to be the U.S. teens, and it is specific to these 12 to 17-year-olds. And the parameter that they are interested in finding out is the proportion P of all U.S. teens with a cell phone. And you want to be very specific when you name these things. So the sample is just going to be the 1,102 12 to 17-year-olds in the survey. And the statistic is going to be the proportion, and it is P hat, which equals 0.71 of the 1,102 surveyed with a cell phone, or who have a cell phone, I should say. So we're not really going to ask all U.S. teens between 12 to 17-year-olds and find the true proportion of the population. We're going to create a sample. This sample happens to have 1,102 12 to 17-year-olds, and then we ask those in the sample. We use that P hat to estimate the true proportion of teens that have a cell phone. So we're creating samples, and one of the things we'll do in the German tank problem is tomorrow we're going to be creating many samples. So let's look at what that means. So what is sampling variability? Sampling variability means that the value of a statistic, and when I say statistic, that's like X bar, it could be your P hat, that kind of thing. The value of a statistic varies in repeated sampling and I'm going to hold off on exploring the Reese's Pieces applet because I'm going to do that with you, so we'll summarize this together. But basically, every time you create a sample, the statistic that you're creating or calculating is going to be a little bit different. So in the activity for the German tank problem, you came up with your formula. If we created a different sample as size 5, you would have a different mean. So if you were using mean, you'd have a different mean to put into your formula. If you were using standard deviation, you would have a different standard deviation for that specific sample. And it's not that anything is being done wrong, it's just that when you create random samples, it happens to vary from sample to sample with regard to the statistic that you're capturing. So what is a sampling distribution? And this is a really important term, so make sure you understand as we talk about this. A sampling distribution of a statistic, that means that I'm looking at X bar, for example. Let's just go with X bar. It is the distribution of all values taken for a certain statistic in all possible samples of the same size from the same population. And like I said, this is extremely important. Okay, we're going to use the sampling distribution applet to look at that and explore that a little bit more. But basically, if you can imagine, you're taking all possible samples of size 5 from our 342 tanks. We now know there are 342 tanks. So every sample that I create is going to be a little bit different. And it depends what I'm trying to compute. I could be looking at the statistic X bar. Every time I create a new sample, I'm going to get a different X bar. And the X bars for every possible sample are actually computed. And a sampling distribution of X bar would be what we'd be looking at. So you have to think of it like this. So think of it like, usually they're going to be sort of normally distributed. We'll talk about that later. But the first time you create a sample, you get X bar sub 1. The second time you get X bar sub 2. The third time X bar sub 3, etc. And you would do that for every possible sample of size 5. So if you want to kind of think about what that is, you're taking 5 from 342 tanks. And that's a really large number. So there's many sample statistics that would be captured if you were actually looking at the true sampling distribution. So let me kind of review that. It's very important. A sampling distribution of a statistic is the distribution of all values taken for a certain statistic. And when I say that, it's like you're looking at X bar, you're looking at P hat, etc. in all possible samples of the same size from the same population. So it's a really important concept as we go into the inference part of the year. Okay, so what is the difference between the distribution of the population, the distribution of the sample, and the sampling distribution of a sample statistic? So essentially, this is an extremely important concept on the AP exam, and understanding the difference between the three will help you approach problems. So when I'm talking about the distribution of a population, this is all that whatever it is you're measuring. Say you're measuring height. It would be all the measurements from the population. Okay? The distribution of the sample is just going to be all measurements from the sample. And the sampling distribution is the hardest one to understand. It is all possible statistics, all values of whatever statistic it is you're looking at. So if I were to complete this up here, and I took every single possible mean from a population. So I looked at size 5, let's just go with size 5, and I took 5 tank serial numbers and averaged them over and over and over and did every single possible one. That is a sampling distribution. So a very different thing than a population distribution and a sample distribution. Okay, when it says sampling distribution, that's when it kind of changes to this really important broad concept. All right, and we'll talk some more about that tomorrow as well. So let's keep going. Now, unbiased estimators. You actually were creating an estimator today in class when you were doing the activity. Okay, And we're going to do a little handout, and we're going to work through some things to help you understand this, but this is just the basics for tonight. An unbiased estimator does not mean perfect. It means that the estimate is not biased. And I'm going to say consistently here. So we're going to explore this with our German tanks. Some of your formulas that you came up with are going to consistently overestimate the true number of tanks. Some of your formulas you came up with are going to consistently underestimate the true number of tanks. Okay, so that's what we're talking about here. So if it's a systematic bias where it's always too high or always too low, that is an unbiased estimator. If many, many random samples were taken and the statistics were average, so it could be X bar, you took every single X bar and you averaged them, or you took every single P hat and you averaged them, it would be roughly the same or equivalent to the true population parameter. Okay. For the estimates to work, the sampling process must be free of bias. So let's kind of go over what I mean by that. You don't want bias, meaning undercoverage, and response, and non-response. Remember what response bias is? It's when for some reason whoever you're surveying is inclined to answer yes or no because they feel guilty. So it could be something like, do you believe that it's unsafe to text while driving? Well, most people are going to say, yes, it's unsafe to text while driving. But they may not truly believe that. They may be lying, and that would overestimate the true proportion of the population who thinks it's unsafe to text while driving, if people are not honest. And then, of course, we have our non-response. For some reason, people just will not answer the questions. A biased estimator systematically overestimates or underestimates the true population parameter. Okay, so we'll come back and talk about some examples later on, once we've done a little bit more exploration. So let's talk about sampling variability. Sampling variability can be reduced to an extent by taking larger samples and using appropriate sampling designs. Okay, for the scenario, it just kind of depends. It could be a random sample. Usually that is a good way to do it. However, sometimes it might be better to do a stratified sample. Now, what effect does the size of the population have on the variability of a statistic? Actually, it doesn't have much effect on it at all, but we're going to review something we learned last unit, which is the 10% condition. So, not much at all, as long as the 10% condition, you can read my writing there, condition is met. And that just means that when you multiply your sample size by 10, it has to be less than or equal to the population size. Okay? Now, what is the difference between accuracy and precision, and how does this relate to bias and variability? So there's two things we're considering here. Accurate means that it's unbiased. Now, some of your formulas may actually sort of average out to give you pretty much the right size or around the same size as the true population of German tanks. Some may be systematically overestimating, underestimating, that kind of thing, and those would not be unbiased. Okay, so that part you probably get. Precise is addressing a different thing. Precision is like low variability. Okay, so we have a couple of scenarios. I'll kind of draw this out for you. Pretend you have a bullseye and you're trying to hit the bullseye. Okay, this is sort of like all the possible outcomes. So here's my bullseye. Now, if my estimates, and remember I told you this, we're going to be creating many samples and using the formula you came up with to come up with a prediction over and over and over. So those are our statistics or our estimates. Now, if you have a situation, let me do this in a different color. If you have a situation where you made a really good formula and it's pretty much spot on a lot of the time, okay? So if you averaged all of your estimates, they would pretty much be on the bullseye. And they're pretty close to the bullseye. You don't have a lot of fluctuation. Now, what if overall you average your estimates and it pretty much equals the true size of the population, but it's more varied? Okay, you can see that as well. And you might have a situation where your estimate is wrong and it's spread out as well. Or you could have a situation where your estimates are wrong, but they're consistent. Okay? So if you look at this, this particular one is low bias and low variability. I'll just call it that. Okay? So low bias, so it's pretty accurate, and it's also low variability. It's pretty precise. This one over here is low in bias. In other words, if I average all these, it's going to pretty much give me that value in the center. But it's high on the variability. Okay? This one down here is high bias and high variability. This is not a good one. You don't want this at all. Okay? And this one is going to be high bias, but low variability. Obviously, you don't want this one either because you're estimating and coming up with a consistent prediction, but it's just wrong every single time. Obviously, this is the best one. And I guess when we talked up here about sampling variability, what we're observing here is sampling variability. So if you witness something like this, you might want to create a larger sample. Okay? So that's pretty much it for today's notes, and like I said, we'll come back and kind of fill in some of the other things in the notes later. Now, I want you to do 1 through 13 odd. The answers are in the book, 17 and 19 as well. So I want you to do all of this for homework tonight, but just kind of read the problem, kind of address it pretty quickly. You can look at the answers, that kind of thing, just making sure you understand today's topic, just to kind of speed you through that a little bit quicker. And I will see you guys tomorrow.